All right, let's just jump right into this explainer on cancer immunotherapy. We are looking at an absolutely fundamental shift in how we approach oncology today. For decades, the standard of care relied heavily on blunt instruments, cutting tumors out, burning them with radiation, or poisoning them with chemotherapy. But the research we're unpacking today reveals a vastly more sophisticated biological approach. I want to kick things off with this quote straight from the source material because it perfectly captures the promise of immunotherapy. We're talking about a dynamic, living treatment rather than a static poison. It dynamically modulates the immune system, meaning it adapts. It doesn't just target one pathway, it literally empowers the body's own defense mechanisms to recognize, hunt down, and clear cancer cells across multiple targets all at once. To see how this actually works, we're going to break it down into 5 key areas: the promise of immunotherapy, cellular therapies, checkpoint inhibitors, tumor resistance, and then finally, where the future of immunotherapy is headed. Section 1. The promise of immunotherapy, shifting the paradigm. The absolutely crucial point here is the paradigm shift itself. We're no longer just attacking the tumor directly. We're actually reprogramming the host's own defenses to do the heavy lifting for us. Moving right into Section 2, cellular therapies, weaponizing the body's defenses. This is our first major category of treatments, adoptive cellular immunotherapy, and we're focusing heavily on natural killer cells and CAR T cells. Okay. Take a look at the delicate biological balance dictating whether a natural killer or NK cell attacks. Right in the middle, you've got this tug of war between killer activation receptors, or KARs, and killer inhibitory receptors, or KIRs. In a normal, healthy cell, inhibitory signals went out, so the NK cell stands down. But when a tumor cell downregulates its MHC1 molecules to hide from standard immune surveillance, it accidentally removes that inhibitory signal. The NK cell realizes something's wrong and activates its killing mechanisms. It's essentially a brilliant evolutionary tripwire.
But, tumors are incredibly smart. They utilize highly specific escape strategies to survive. For instance, they'll upregulate molecules like HLA-G to forcefully bind to the NK cell's inhibitory receptors, basically putting the immune cell right to sleep. Even more devious, tumors will shed decoy proteins like MIK and MICB straight into the microenvironment. The NK cells attack the decoys instead of the actual tumor. Because of this, researchers are now actively developing targeted antibodies specifically designed to stop this shedding process and keep NK cells locked onto their true targets.
So that brings us to CAR T therapy, which is honestly a titan of cellular immunotherapy. The process is fascinating. You extract a patient's own T cells, use genetic engineering to give them chimeric antigen receptors, which is basically a brand new tracking system for specific tumor antigens like CD19, and then infuse them back in. Now, CAR T therapy has shown massive, unprecedented success in blood cancers like B-cell acute leukemia. But, and this is a major limitation, it severely struggles in solid tumors. One major reason is the harsh tumor microenvironment, which leads to a frustrating phenomenon called T-cell depletion or exhaustion. To get around this T-cell depletion in solid tumors, researchers are exploring some incredibly fascinating epigenetic and genetic tweaks. For example, disrupting the TET2 gene can actually lock T cells into a central memory state, extending their active lifespan. Scientists are also looking at inhibiting NR4A transcription factors, which normally drive that exhaustion, or using epigenetic drugs like decitabine to literally reverse T-cell depletion. The whole goal is to keep these engineered cells fighting longer and harder in that highly toxic tumor microenvironment. All right, Section 3, Immune Checkpoint Inhibitors, releasing the immune system's brakes. If cellular therapies are about building better soldiers, ICIs are about removing the barriers holding your existing soldiers back. These are arguably the most famous immunotherapies on the market today. This perfectly maps out the classic brakes and accelerators analogy. Up top, you see that for a T cell to activate, it needs an accelerator, the CD28 receptor binding to B7. But the body has built-in brakes, like the CTLA4 receptor, which aggressively competes to bind with B7 first, shutting the T cell down to prevent autoimmune damage, and tumors completely exploit this. Down below, we see the PD-1 receptor on the T cell binding to PD-L1 on the tumor, which again turns the T cell off. Immune checkpoint inhibitors are brilliantly simple in concept. They're just antibodies that block these connections. They literally take the foot off the brake so the T cell can resume its attack on the cancer.
Now, while both act as brake releases, they operate very differently. Blocking PD-1 or PD-L1 is highly selective. Because it acts directly within the tumor tissue during the late effect stage, it generally has fewer severe side effects. On the flip side, blocking CTLA4 acts upstream in the lymphatic tissues. It promotes early T-cell activation across the board. The downside? You're removing the brakes from the entire immune system, which frequently leads to severe autoimmune reactions like colitis, hepatitis, and thyroiditis.
Looking at the major clinical players here, like Keytruda and Yervoy, researchers are finding that combination therapies are the real key. By pairing an anti-CTLA4 to build a massive army of T cells in the lymph nodes, with an anti-PD-1 to ensure they don't get deactivated once they reach the tumor, we can significantly boost the overall anti-tumor effect. By striking at multiple checkpoints, we literally stop the tumor from simply switching its defense strategy.
But this brings us to the million-dollar question, right? The dark side of this double-edged sword. If these drugs are biologically revolutionary, why are they still failing in so many patients? Why is the clinical response rate for solid tumors often hovering around just 10 to 30%?
Which brings us to Section 4, Mechanisms of Tumor Resistance, the Evolutionary Arms Race. We are essentially watching a real-time battle where the tumor rapidly mutates and adapts to evade our absolute best therapies. Tumors orchestrate a complete immune escape through a multi-front war. You've got mechanisms altering immune cell recognition, direct cell-to-cell signaling manipulation, and even tumors exporting their defenses directly into the bloodstream. It's not just a passive lump of tissue, right? It's actively fighting back. Let's break these down. So, tumors generally utilize two types of resistance, primary and acquired. Primary resistance means the tumor already has genetic mutations causing massive PD-L1 expression before the treatment even begins. The T cells are depleted early on. But acquired resistance is incredibly ironic. When your immune system mounts an attack, your T cells secrete a chemical weapon called interferon gamma. But this very act of releasing interferon gamma actually signals the tumor to start expressing PD-L1 to shield itself. The immune system's own attack literally triggers the tumor's defense. And then there's one of the most surprising findings in recent research, self-neutralization. Sometimes, clinical tests will show a tumor has massive amounts of the target, PD-L1, but the drugs completely fail anyway. Why? Well, the tumor cells will actually express both PD-1 and PD-L1 on their own surface. These molecules bind to each other on the same cell, creating a closed loop. By the time you inject the immunotherapy drug, there are literally no free targets left to hit. The drug is effectively locked out. This same frustrating mechanism can even happen on the body's own antigen-presenting cells. It gets crazier because tumors can also launch long-range attacks. As we saw earlier, tumors secrete exosomes, tiny little lipid bubbles covered in PD-L1 directly into the blood circulation. Think of them as biological interceptor drones. They float through the bloodstream, finding and neutralizing circulating T cells long before those immune cells can even travel to the physical site of the cancer.
Finally, Section 5, the future of immunotherapy, pros, cons, and beyond. Weighing these incredible biological mechanisms against the stark realities of tumor resistance, where exactly does the future of this field lie? How do we maximize the benefit while minimizing the failures?
As this breaks down, immunotherapy really is a true double-edged sword. On the advantage side, for patients with hot immune-inflammatory tumors, this therapy offers highly accurate, long-term eradication of microscopic lesions. It's basically as close to a cure as we can get. But the disadvantages are very real. For immune desert tumors, it does almost nothing. And when it goes wrong, it carries severe risks of autoimmune toxicity and even a terrifying condition called hyperprogressive disease, where the treatment accidentally accelerates tumor growth and death, not to mention the staggering financial costs. To mitigate those risks and ensure the right patients get the right drugs, the future relies entirely on predictive biomarkers and precision medicine. We're moving toward liquid biopsies to measure blood tumor mutational burden, because higher mutation rates usually mean more targets for the immune system. We're measuring intratumoral heterogeneity, looking for clonal neoantigens. We can even use advanced cytometry to measure specific CD14+ monocytes in the blood to accurately predict patient survival. We are no longer guessing. We're profiling the tumor at an incredibly granular level. And incredibly, I love this part, this precise profiling all ties back to a totally unexpected place, your gut. Research definitively shows that the abundance and type of commensal intestinal flora directly dictate how well you'll respond to anti-PD-1 therapies. Patients with robust, healthy microbiomes respond significantly better to immunotherapy. This reveals a massive clinical takeaway. Broad-spectrum antibiotics, which completely decimate your gut flora, can literally destroy the efficacy of your cancer immunotherapy, and absolutely must be avoided when possible. It's a fully connected, holistic system. This leaves us with a highly provocative final question as we wrap up this explainer. As we uncover new, powerful immunosuppressive targets like Siglec-15 and learn how to manipulate the gut microbiome to our advantage, how close are we to cracking the ultimate code? How fast can we take every untreatable immunosuppressive, cold tumor and artificially turn it into a highly curable, hot one? The paradigm has undeniably shifted, and the next decade of this biological arms race is going to be absolutely incredible to watch.